Hello everyone, my name is Mingyang. It's a great pleasure for me to have this chance to share my research with you. My topic is investigation of the effect of porosity on intergranular brittle fracture using peridynamics. My presentation will be basically divided into 5 parts. First of all, there will be a brief introduction about porosity. Then peridynamic theory and our peridynamic model for cubic polycrystals will be introduced. More importantly, we will use this model to investigate the influence of porosity on the fracture behaviors, and some conclusions will be drawn during this section according to our observations. Finally, we will show some potential directions for our future research. As we all know, porosity exists in numerous materials, no matter its nature or man-made. According to the recent research, porosity can degrade some material properties, less the fatigue resistance, and it may also lead to fracture or damage of the materials. However, the effect of porosity is still not fully understood, which mainly because porosity usually is in micro-scale level. Therefore, it would be quite necessary for us to focus on such aspect. In order to research about the fracture behavior related to porosity, we prefer to use peridynamic theory. The traditional classical theory based on partial differential equation is not easy and convenient to deal with the discontinuous problems. Although there are many match-free methods generated to solve this problem, usually they are still quite complex. Peridynamics is improved from this match-free method and is created by Dr. Selda in 2001. The governing equation of peridynamics is kind of integral equations, which means it allows us to solve the fracture problems easily. In peridynamics, stretch is specifically defined to judge the break of the bonds between peridynamic points. If the stretch is larger than the critical stretch, which is calculated from the fracture toughness, the interaction between these two peridynamic points will be judged as break. Then, the local damage can be calculated. If the damage parameter is equal to 1, it means that this point entirely loses connection with other points. Based on bond-based peridynamics, we found a model for cubic polycrystals. There will be 2 types of bonds. On the one hand, fiber-reinforced bonds will be defined according to the orientation of the crystal. On the other hand, there will be material bonds in all directions. The diagram on the right-hand side is an example of the bond distribution for horizontal crystal orientation. After balancing the strain energy density between peridynamic and classical theory, and combining with the plane stress assumption, finally, we can successfully obtain the bond constant for 2 different kinds of bonds. This model has been successfully applied to analyze the stress current cracking and pitting current phenomena. Besides, ice interaction analysis can also be performed by using this model. Recently, this model has been further extended to stand thermal loadings. The polycrystals are generated by Verney tessellation method. The seeds will be randomly spreaded through the plate, and by judging the distance from the peridynamic points to these seeds, each peridynamic point will find their specific grains. Here is an example for proving the accuracy of our model. The plate consists of 100 grains and is fully constrained on the left-hand side. tension loading is applied on the right-hand side. The displacement in the horizontal center line and the vertical center line is collected for comparison. And from the two plots on the right-hand side, we can see the results from Peridynamic match well with the result from finite element analysis. Then, we utilized our model to explore the effect of porosity. The plate is made of steel, and its size is 5 mm times 5 mm. There will be two small initial cracks at top and bottom edge of the plate. 25 meter per second velocity is applied through additional 3 layers of peridynamic points as loading conditions. There will be 2000 time steps, and for each time step, the time length is 1 nanosecond. For the porosity, the diameter is decided as 0.2 mm, and they will be randomly distributed at grain boundary. First of all, let's have a look at how the crack propagates when there is no porosity. Most of the crack is generated from the pre-existing crack and concentrated in the central region of the plate. When 16 porosity is created in the plate, we can see that for the main crack, it still propagates towards the opposite edge. But the difference is that the main crack becomes more willing to propagate towards the porosity, and the branches of the main crack is slightly reduced. What's more, there are small cracks initiated from the porosity, and the direction of the crack propagation is perpendicular to the loading directions. Eventually, this small crack will propagate through the grain boundary to form new generated branches of crack. Last but not least, the more intensive the pulse, the more serious the new created crack. The plots of the damage at 4 time stage are also presented to give a more clear illustration about how the crack propagates against the time. Additionally, another case which has the same grain distribution but different porosity locations is performed. This time, it can be witnessed that all of the previously mentioned features can still be captured. Furthermore, an additional case which, with both different distribution of grains and porosity, is given to further test whether these features will be affected. But it seems that, according to these two cases, these fracture behaviors will not be significantly influenced by the distribution of the grains or porosity. From what has been shown, we can conclude that porosity will initiate small crack, and they will propagate perpendicular to the loading directions to form new branches of crack. And if the porosity is intensive, this phenomenon will become more clear. The propagation of the major crack has also been changed. It prefers to propagate towards the porosity, and the branches has also been reduced. Finally, grain distribution or porosity distribution will not have big influence on these observations. Another 3 cases are added to explore the effect of the grain numbers, percentage of porosity, and also the grain boundary strength. First of all, the number of the grains is reduced to 100 and then 50. When the grain number is 100, although the severity of the fracture is decreased, the change is not obvious. But when it comes to 50, only the major crack is clearly kept. Here are the plots for the damage at the final time step. Next, the porosity increased from 2% to 5% gradually. For 3%, the change is not big, but with the increase of the porosity, the severity of the fracture, especially the main crack, become increasingly serious. We also put the final stage of the damage for different percentages together, and they can also support our observation. Finally, we increased the green boundary coefficient from 0.5 to 1. Green boundary coefficient is the ratio of the bond strength at green boundary to the bond strength inside the greens. By doing so, the microscale will become more identical to the macroscopic material, and we can see that the behavior of the main crack has converged from intergranular to transgranular. In conclusion, severity of the crack, especially the new created crack, is positively in proportional to the green numbers and porosity. For the green boundary strength, with the increase of the green boundary coefficient, the influence of the green boundary coefficient will decrease, and the fracture become more similar to the macroscopic pattern. For the future research, we are planning to focus on one typical material, uranium dioxide, which is heavily suffering porosity problem, and at the same time, we'll explore the influence of the porosity when it's not just distributed at the green boundaries. The relationship between the microscale and macroscale modeling for the fracture behaviors will also be researched. Thank you very much for listening.